there are a lot of applications for the Bernoulli's equations. As here, I just pick up some ideas. As you see, this is we call that is stagnation tube. Why we call that is stagnation? Because usually the flow if touch the tube in here, the flow if touch the tube in here, the velocity is equal to 0. So that's why we call it is a stagnation tube. So if we know the velocity in here is 0, and we have because we put the tube into the waters over liquid, and we can observe some rising highs in the tube. So can we answer the velocities for these problems? That means if we have the higher liquid high, and can we answer how large flow velocity along the string lines? So we would like to answer the V0. So just based on the Bernoulli equation, we have 1 0 in here and 1 in here, and we call that is a stagnation tube. So we put the tube inside, and we are trying to answer the velocities at this point. Okay, so follow the Bernoulli equation. We know the pressures 0 plus gamma Z0 and the plus 2 over rho V0 squared. And here we know the P1 and the plus gamma Z1 and the plus 2 over rho V1 squared. Okay, and we tell you this is a stagnation tube. So in here we don't have the velocities. So in that way, this is equal to 0. And then, so can we answer how large for the V0 in here? So we know this is piezometric pressure for the Z0 point, and minus the point 1, and then, oh sorry, I because our question is focused on the V0, so I keep the V0 in here. So we know 2 over rho V0 squared is equal to the piezometric pressure P1 minus this, I move to the right, minus PZ0, okay? And then the V0 squared and equal to the 2 and rho, and the upper is PZ1 minus PZ2. Okay, and we know the PZ1 is equal to gamma H header, the H header 1, and minus gamma H header 2. Okay, so what is the head? The head height for the 0. Oh, sorry, I changed the. This is 0. This is 0. Okay, so what is the head 1? The head 1, that means the point in here. So the head 1 is the total height is L plus D. It's for the head 1 is L plus D. And what is head 0? The head 0 is in here. So you see the water depth only have the D, right? We only have the water depth D. So the head 2, oh sorry, head 0 is D. Okay, so we put the header number to the equations. So here is 2, and I move the gamma outside. The gamma and the inside we only have the L plus D minus the D. Okay, and then we know the gamma is low G, so low can cancel out. So here we only have the 2G and L. So finally, you know the velocity V0 is root 2GL. Okay, so the idea for the stagnation tube is trying to measure the velocity of the flow. If we can observe the height changes, and then we can quickly to compute how large the flow velocity. So you just check the L and follow this equation, and we can estimate the flow velocity very quickly. Okay, so this is just based on the Bernoulli equation, and we can calculate the flow velocity very quickly. Okay, and the second idea we call that is a Pitot Tube. Okay, Pitot Tube, and then just a Pitot Tube just puts the stagnation tube inside. So we have the pipe inside is stagnation tube. Okay, and we have the pipe outer pipe. The outer pipe is traditional static pressure tube. Okay, so we can measure the static pressures and the inside pressures. So based on the Pitot tube, we can have the pressure difference. If we can measure the pressure difference inside and outside, and we still can estimate the velocities in here. So this is the flow velocities. So the idea also based on the Bernoulli equations. So we have the P1, gamma, Z1, and the 2 over rho V1 squared. And this is a P2, gamma, Z2, and the 2 over rho V2 squared. So the idea is because the inner pipe is stagnation tube. Stagnation tube in here, the point in here, the V always equal to 0. Okay, so we don't have these items. So the question is, what is the V2 velocities along these straight lines? Okay, so we have the this is a piezometric pressure for the location 1 and the piezometric pressure for the location 2. So delta P is P1 minus piezometric P1 minus piezometric P2, and we have the delta P. And delta P finally is equal to 2 over rho V2 squared. So we can reorganize the V2 is equal to 2 times delta P changes divided the rho. So if we put the Pitot tube, we can have the pressure difference. So the outer pipe, this is static pressure tube, trying to measure the piezometric pressures for the point 2. And we put the inner pipe is a stagnation tube, trying to measure the P1 pressures. But it's for the piezometric P1 pressures. So we have a Pitot tube can tell you the location pressures for the 2 and 1 very quickly. So if you can look the pressure difference, and you can compute the flow velocity very quickly at the location 2 point. Okay, so this is the idea for the Pitot tube. So following these ideas, so the questions, the figure tell you, can you answer how large flow velocity in here? How large flow velocity in here? And then you see this is a Pitot the questions, the figure showing here, the user put the Pitot tube inside the flow, and you can observe some deflections of the mercury liquid inside here. So can you estimate the flow velocity? So based on the flow velocity, we know it's equal to 2 times pressure difference, right? And divided the liquid densities. So if you can compute the pressures and the difference, and if you know the density, and you can estimate the flow velocity, right? So the question in here, can we compute the differential pressures? Okay, so how changes pressures from 1 to 2 points. So in here, based on the hydrostatic equation, we know this is the P, this is the P1, right? And the P1 to here, so we have the pressure 1, and because the elevation is decreased to here, the elevation is wait, we need to consider the location start from here. So because the elevation is start from D1 minus D2 and L in here, so we know the total length difference. We need to elevation change here to here. So how many elevation changes? So, and the liquid in here is kerosene. Okay, the liquid in here is the kerosene. So because the elevation decrease, so the pressure increase. So in here we have a gamma kerosenes, gamma K, the kerosenes, plus D1 minus D2 plus L, right? Because the total length, and because the elevation decrease, so the pressure increase. So I use the plus in here. And then in here, we make the balance, and we would like to change the elevation to here. We would like to change the elevation from here to here. Because elevation is increased, so here is the minus, and the liquid is the mercury. So this is the gamma M and the Y in here. Okay, and finally we would like to go back from this point, go back to here. From this point, go back to here. So this is the L. Okay, in here this is L minus Y. The length start from this point to this point is L minus Y. And what is the liquid? The liquid in this length, along this length, is kerosene. So here is also minus kerosene, L minus Y, and finally equal to P2. Okay, this is equation. I just follow the hydrostatic equation because we know that elevation decrease and pressure increase. If elevation increase, the pressure decrease. So that here is plus, minus, minus. Okay. Okay. So we expand this equation. So P1 plus gamma K Z1 and minus gamma K Z2 and plus gamma K L. I just in here, and later is minus gamma M Y and minus gamma K L and plus gamma K Y, and finally equal to P2. pressures. Okay, so then we take a look. Some item can cancel out. For example, in here, KL and minus KL, so we cancel out. Okay, and then I just put the label. They are the same, and put they together. For example, here is a P1 Z1. Okay, it's a P1 Z1. So for the P1 Z1, so here is a piezometric pressure at the location 1. And you see, if I move the P2 to the left hand side, so will be the minus P2 plus gamma K Z2. And this is piezometric for the D2. Okay, piezometric for location 2. And then we take a look. We still have some, so we already used these items. So we still have some items related to the Y, deflection Y. So I plus Y, and then inside is the gamma K minus gamma N, and equal to 0. Equal to 0. So actually we know the pressure difference. This is the pressure difference. This is the delta P, what we want to have. This is the delta P we want to have. And the delta P is equal to Y, because we move this item to the right hand side. So I change the order is gamma N minus the gamma K. Okay? And we know the question only tell you the SG specific gravity numbers in here. So we can rewrite this is Y inside is gamma W because it's a mercury. Mercury is SGN, and minus gamma W. Gamma W is water, okay? Specific weight for the water, and SG K, okay? Follow these equations. So we know the delta P, we put the gamma outside. So gamma WY multiply SGN minus SGK. Okay? So what is the density? And we need to use the mercury or the kerosene. The density showing here. We need to use the kerosene, right? Because we are discussing the flow velocity in here. We don't discuss the velocity in here. So the density is the kerosene densities. So we know the kerosene density because we don't have the density of the kerosene, but we have the SG numbers. So we know SG kerosenes multiplied the rho W is equal to rho K. Is equal to rho K. So we already prepared the delta P and the delta K. So follow this equation. We can have the V is 2 times delta P divided rho, and we put the delta P and the rho inside these equations. So we have the 2 times gamma W Y SGN minus SGK divided rho. The rho is SGK multiply rho W. Okay, and then we know the gamma W is rho G. So the rho W can cancel out. So we can summarize it's 2 times G Y and SGN minus SGK SGK divided SGK. Okay, so you can check. You know the SGK is 0.81 and the SGM is 13.55. And what is the Y? Y is the deflection height. Deflection height in here 7 inch. But we need to transfer the inch to the FT, right? We need to transfer the 7 inch to FT. So you need to convert. You divided the 12 because 1 FT is equal to 12 inch. So you need to transfer the deflection height, this is Y, to FT unit. And what is the G? As I mentioned, the G, the unit for the imperial unit, G in here is 32.2 FT divided second square. So you put all of the number inside the equations, and then finally you will have the answers. Okay, so so we need to still remember the hydrostatic idea. If we don't have the hydrostatic idea, we cannot compute the delta P for these questions. So since we have the delta P and then we know the rho, so we can compute the velocity. Okay, so I don't have time, so you can calculate the answer by yourself. Okay, and then you can check. Maybe some location is not correct, and then you can modify by yourself. Okay, so this is another questions, but we change. Previous questions exercise focus on the liquid, but this exercise we are discuss with the air. Okay, so as you can see here is wind tunnels. Okay, so because there is some airflow in the tunnels, so we have the airflow in the tunnels, and we put the Pitot tube inside, and the question directly tell you how large delta P difference. So we exactly know the delta P in here. So what are the questions? The questions only have the rho. We didn't know the rho in these problems. So because this problem is the medium is air, so we need to follow the ideal gas law. So if we based on the ideal gas law, we know the government equation is P is equal to rho RT. Okay, so only unknown parameter is rho in here. So if we can base on this equation, so we can compute the rho for our medium air. Okay, so the rho is actually equal to P divided RT. And I already tell you the answer, the question provide how large pressures, absolute pressures inside. So we know the absolute pressure is 98 kilopascal. So here is 1,000. And what is the gas constant is 208 sevens. And the temperature is with the 20 degrees. And we need to convert to the absolute temperatures. So we need to 273 plus 20 degrees. And you can compute how large densities of the airs. Okay, so use my calculators. So the final density for me is 1.165. Okay, so the unit is the kilograms per meter cubic, right? So it's quite close to the normal conditions. For the air density is 1.2, but a little bit smaller than normal conditions. So already you have the delta P in here. So the 2 times delta P divided the density 1.165, and you know the velocities. Okay, so I used my calculator to compute the answers. And for me, the answer is around the 35.4 meter per second. Okay, so the importance in here, the key knowledge, why we know these equations, because we derive these equations based on Bernoulli's. And Bernoulli tells us the pressure difference and the velocity will also change it. So usually the pressure decrease and the velocity increase, because we based on the Bernoulli equation satisfy the energy balance. Okay, so this is our final exercise for the Bernoulli equations. So the next semester we have laboratory experiments, and this is the experiments related to the Bernoulli equations. Okay, so as you see here, we have the ventaries in here, and you see, if you take a look, there are different cross-section areas. In here is a small, but the other place is a larger ones. So we have a different cross-section area. We have different velocities along different cross-sections. And there one pipe. As you see, this is the pipe connect to the pressure gauge. So you can check the pressure in here. You can check the pressure in here. So you can compute, you can know the delta P very quickly, because there are the pressures recorded in here. And this is Pitot Tube. And you can change the Pitot Tube at the different locations. So if the Pitot Tube at a different location, we have different velocities. Okay, and the different velocity, you can observe the different delta P recorded in here. Okay, so it's just if we have the cartons figure in here, so we fix the width. This is the maximum width of the cross sections, and this is the smallest width for the cross sections. And the idea is we put the tube, Pitot Tube, at the different location, maybe in here. If I change the Pitot Tube, maybe in here. So different location, we have different pressures. And different pressure, you can observe some different pressure in here. And based on the equation, you know the pressure difference 2 times divided the liquid densities, we know exactly the velocities at the different locations. Okay, so this is our experiment. So the idea is just follow the Bernoulli's. Okay, why I always repeat and introduce the laboratory experiments here, because in next semesters, totally you will forget anything. It is what you learn from these semesters. And then, but the next semester we have the experiment, right? And you will stand on the experiment, and you don't know what you need to do. And you don't know, you forgot the principles, everything you forgot. So I highlight some importance and the key concept in here. In that semester, if you forgot anything, you just open the PPT file and try to remind anything. Okay? So some equation showing here in next semester you will forget. But you know this equation is based on Bernoulli ideas. So that's why you have these equations. Okay, so we still have a time. So now we have some concept for the rotations. So previous slides we always tell you we don't mention the rotations. We always consider the flow is linear flow, not rotate. So if we consider the flow start to rotate, can we identify is rotational flow or not? So we need some equation to identify the flow condition is rotational or not. So before that, we need to define what is rotate and how large for the rotational flow. So for this idea, you see, this is a Coulter flow. You know in chapter 2. And when we discuss the Coulter flow, we are apply the viscosity equations. Because the viscosity tell you the shear stress is equal to the viscosity, dynamic viscosity, multiply the velocity gradient. And this is the velocity gradient. The velocity change when the y increase. And this direction is along the u axis. Okay? So in that, why I put the Coulter flow in here? That means the Coulter flow is rotational flow. If you see these figures, you know why the Coulter flow is rotation. Because all of the flow direction is x-axis, along the x-axis, and the increase when the y location increase. So the flow will have this character-wise rotate because the flow velocity like this shape. So if the character-wise flow rotations, the direction is inside the papers. The direction is inside the papers. The rotation axis is inside. Use your right hand. Okay. So the idea is if you can quantify the theta change with the time. So we can. That means if you have the theta 1 and you have the theta 2 and you have the T1, T2, and you can compute the theta rate. And if the theta rate is equal 0, that means the flow is not rotational flow. If the theta rate not equal to 0, that means the flow is rotational flow. Okay, so the idea is, can we quantify or can we compute the theta rate? If we can, so we can identify the flow condition is rotational or not. Okay, so but you take a look here, the theta. What is the theta? The theta is, this is bisectors. Okay, the line, and the bisector line, and this is horizontal line. The angle between the bisector and the horizontal is the theta. Okay, so we define the theta is a bisector line with the angle theta relatively to the x-axis directions. Okay, so the idea, how can we compute the theta rate? So based on these cartoon figures, so you have the theta B and the theta A, and I tell you if the theta rate is equal to 2/1 theta rate A and the theta rate B. So the key questions in here, can we have the theta A and the theta B? If we can, we can compute the theta rate. Okay, so for these figures, you see this is bisectors 9. And the bisector 9 with the angle relatively to the x directions is theta. So here, what is the beta? If based on this figure, can you identify how large the beta it is? So we know that this angle is 90 degrees. So what is the beta? The beta is 2 over pi. I use the radial length. The 90 degrees is equal to pi divided 2. The 90 degree. Okay, 90 degree if minus theta A, right? Minus theta A is here, plus theta B is equal to beta, right? Is equal to beta. And because I use the bisectors, so you know the theta. What is the theta? Bisector. So here, I know here is 2 over beta, right? Because this line is bisectors. So I know here is beta divided 2. And if 2 over beta plus theta A will equal to theta, right? Bisectors and half beta plus theta A is equal to theta. Okay, so I expand this equation because this I know that 2 over beta is equal to 4 over pi here, and the minus 2 over theta A, and the plus 2 over theta B, and here plus theta A. Okay, and then here is the 4 over pi minus 2 over theta A, and here is plus theta A. The total is 2 over theta A, and keep here 2 over theta B. So how about the theta rate? So we need to have the differential time, right? D theta, or you can say delta, the theta if divided delta t, and we have the theta rate, right? So we have the theta rate, and because the 4 over pi is not the function of the time, so if we take the differential of the time, there didn't changes. The 4 over pi didn't changes. So we only have a 2 over 1 theta A rate plus theta B rate. So follow these questions. If we can identify the theta A rate and the theta B rate, we know how large the theta rate. And I tell you the theta rate equal to 0. That means the flow is not rotational flow. Okay, so next class I will tell you how to compute the theta A and the theta B rate. And then you can compute the theta rate, and to identify the flow condition, rotational or not rotational. Okay, so we may stop here and prepare your